Okay, we are quite at the end of the first part of this course, and as I told you in the first lessons, the first part is connected to the development of tools. Tools to study the signal, to study the noise. In this lesson we will concentrate about the concept related to the filtering signal. In the next one we will introduce some concept about the filtering noise, and then we will start with the development of all the filters. So, in these slides we will start from the discrete time filtering, then we will move with the continuous time. We will study the weighting filter, weighting function. We will define the weighting function both in the time domain and in frequency domain, both for time constant and time variant filter. So, how we can start? We start from a very simple scheme, the scheme that we introduced in the first lesson. I mean, sensor, preamplifier, filtering. At this moment we are interested just in filtering, so we have an input signal X and an output filter signal Y. That's it, and then a meter, obviously. So we are studying linear filter, so we can use the superposition of the effect, and we start from the digital one, I mean a discrete time one. Why? Because it's easier to understand, and it's the filter that you can use, for example, in DSP, FPGA, microcontroller, or something similar. Which is the definition of discrete time filtering? I mean, the output is the weighted sum of the input value X taken at the values time alpha. The weight does not depend on the input X. We will go back on this point in 30 seconds. So, go back. The output is the weighted sum of the input value X taken at various times alpha. So we can easily write this equation. Again, we are speaking about at this moment discrete time filtering. So the filtering that we can use, for example, with DSP. So let's try to write the output. The output here, so here's output at time Tm is equal to the sum, as you can see here, the sum of the value X of the input times the weight that I use for that particular time. So I can write in a compact way the sum here, and so if you prefer, this is the result. So we can distinguish, we have different scenario depending on the value of the weighting value W. If the weights are the same WK for any Tm, you can see here for any Tm I define a sum. If the weight are the same for any Tm, so for any acquisition times, I'm speaking about constant parameter filtering. If I change the weight as a function of Tm, we are speaking about non-constant parameter filter. I told you that we have to go back to this sentence, weights that not depend on input X. A totally different thing is a filter where the weight doesn't depend on Tm, but depends on X. In this case, we will speak about adaptive filter. I mean, a filter that changes the weight as a function of the input itself. We will not speak about adaptive filter. We will always speak about constant parameter, where the WK is always the same, or not constant parameter, where I change WK as a function of Tm, not X, Tm. So, let's go on with our system, and let's try to define the weighting, the sum with different weight. So this is the input. I have alpha 1, alpha 2, alpha 3, and so on, that are the sample that I have to use, that I would like to use for my filter. So what I have to do? Then I have to decide the weight for each sample. So here, for example, I could define the weight for each sample. For this weight here for this sample, this mole here for alpha 1, and so on. As you can see, it's normal that the weight value is higher for TM. Yes, probably yes. If you think about a filter, you are extracting from the sample your output. I suppose that it's normal that you have a higher weight for a sample that is near to your measurement time, and you wait you gave a very small value for something that happened very far away in time from you. So we have the sample, we have the value for each sample. We have just to multiply the x of alpha 1 times w1, x of alpha 2 times w2, and sum all the value. So we can create our output at Tm time. Very basic concept. It's exactly what you do in an FPGA, DSP, microcontroller with a digital approach. So we can write the sum in that way, in a very compact way, but let's try to move from this discrete time approach to the continuous time signal filtering, because I will show you in the future that the better results is obtained with continuous filtering. So on the left we have instead of the discrete values, with alpha of w of k and x of k, because we are sampling some precise point, and then we are summing the product of wk times hk, and we are making the sum. In the continuous times, we will have probably the product again with a function and the function x, and instead of make the sum, we will make the integral, like any other moving from discrete time to continuous time. So let's try to do the same things in the continuous time. So the input is always the same, but at this time we have no more the sample, we have just a continuous signal. At the same time, at this time, we have no more some weight for in the discrete time, but we will have a continuous function. So we take Tm here and we apply the weighting function here that give us the weight for each delta alpha. So let's try to compute the output at the value Tm. Exactly like for the discrete time, we will take a sample. This time we are in the continuous time, so we have h of alpha times d alpha instead of the single sample. Then we have to multiply for the weighting function and then make the integral to obtain the output. So we obtain this value here, give us this value, then we have to make the sum, and so the integral for all the value. Here you can find the integral. So the concept is exactly the same for the discrete time. So I told you about weighting function. If you go back, this function here is the weighting function. Why? Because they give us the weight for each d alpha or each sample, if you prefer. So is it possible to write some definition, better definition of the weighting function? Obviously yes. By the way, we call the weighting function also memory function. Why? In both the cases, if you think about the name weighting function, memory function, give us an information of how the system wait or remember the past. This is the reason because we call weighting function or memory function. So a weighting function is defined which for every element x of alpha in the alpha of the input denotes the weight w of alpha given by the filter. So if we write the output, we can write the memory function in this way. The output of Tm is the integral from minus infinity to Tm of the weighting function time our input in the alpha. Alpha or is our time. So again, this is the input, This is Tm, this is the weighting function that I multiply each T alpha and make the integral and obtain the results. Okay, this is the generic approach, but the question is, can I write it for something that I perfectly know, for example, a low-pass filter? So let's try to do that with constant parameter linear filters. What is a constant parameter linear filter? It's a filter where the weighting function doesn't change as a function of Tm. It's exactly, for example, our standard low-pass filter that you perfectly know, RC. So let's start with an RC. So we take an RC, for example, here. So I have an input and I have an output. So what I can say, I can say that I can create point by point my weighting function. Let's try to understand how I can do that. So it's quite a graphical point of view. This is the t-axis, which is the rules to create the weighting function. This one, you have t and you have tm and at times alpha 1. So you take a delta here at times alpha 1, so t minus alpha 1, this delta here. Then you write the delta response of our system at that time, shifted at that time, so h of t minus alpha 1. You perfectly know that the delta response of the low-pass filter is the exponential decay time. So we are here, we write just the decay time, okay, and then we take the value of the weighting function shifted at this time here, and then this is the value of the weighting function at alpha 1 value. That's it. If we reconstruct this method for all the points, we can find the weighting function. Let's try to with another point. I would like to use to understand this point, so alpha 2. So what I have to do, I have a delta, so again here I write the delta response here, so the delta response is something like this. So I take the value that this time is this one here, and I put this value in the place of alpha 2. Okay, that is exactly this value here. So I can do that for all the time. Okay, the graph here is quite awful, and I can reconstruct all the different points. I will obtain exactly this function. So this is a method to write down the weighting function for a constant parameter filter. As you can see, it's really easy. So we are speaking about constant parameter filter. So with a constant parameter filter, a good thing is that if I consider Tm1, so the measurement time 1, I can write the weighting function. Okay, that is h of Tm1 minus alpha. Because we develop the function in this way. But let's try to consider another time, Tm2 for example. With the Tm2 I can replicate exactly the same concept, and since we are speaking about a constant parameter filter, I will obtain exactly the same function, but it's shifted. This is a key point for the constant parameter filter. It's not always valid for any filter. It's valid only for constant parameter filter, the filter that you are used to work with. So this is an important property of this filter. My old professor, Professor Serjakov, always thought something like this here. In other words, when Tm is changed, the weighting function changes in a very simple way. It works with the Tm just like a tethered dog follow his boss. So with a constant parameter filter, the weighting function for any Tm has always the same shape and always the same position respect to Tm. As you can see here, this is Tm and this is the weighting function. This is Tm and this is the weighting function. So it's very simple, and it's the filter, the delta response or the weighting function that you are used to use with low-pass filter or any standard filter. So let's go on, and you remember that the weighting, let's go try to have a deep insight in the weighting function, and you perfectly know that the output signal of the low-pass filter, we saw that is the convolution between the input and the delta response. So we define the weighting function as h of Tm minus alpha. Let's try to demonstrate. We did that from the graphical point of view, because I give you a method. Say, okay, you have a delta, write the shift the delta response, take that value, report that value, and in this way we write that the weighting function is the delta response shifted and mirrored. It's possible to demonstrate that this is exactly the weighting function? Obviously. We have just to use the definition. This is the definition of the weighting function. The output at the time Tm is the integral from minus infinity to Tm of the input x of alpha times w of alpha. Okay? But you know also that the output is the convolution of the input times h of t. So we write the convolution from is the integral from minus infinity to Tm of h of alpha times x of alpha times h of Tm and alpha. So since these two equations give us exactly the same number, the same output, we can define the weighting function exactly like h of Tm and alpha minus alpha. So from the graphical point of view and from the mathematical point of view, obviously we have to obtain exactly the same results. So this is correct for the constant parameter filter. My question is, what happens if I have a time variant linear filter? A time variant linear filter is a filter where the weight is not the same for any position, any time. So how I can create this filter to try to play and to understand? So let's try, for example, to use a very simple filter, an RC, like the previous one, so low pass filter, but this time I'm including a switch. Why? Just to create something that changes. I will show in the future that this switch is really important. We will create different filters with this switch, but at this moment it's very simple. R, C and switch. That's it. Obviously, I have to define the behavior of the switch. So the switch has this behavior. Here is closed. Then at this time I open the switch, and then I close the switch. That's it. How I can create the weighting function? Exactly the same way that we use for the constant parameter filter. So I take one time Tm, the measurement time, then I take a delta at t minus alpha 1. I write the delta response here, and I obtain the value at Tm. I can do that for example, different time. By the way, in this case you have to pay attention because, okay, here we have an RC. What happened if I apply a delta at this time? The delta at this time, the switch is closed, so I will have the delta response normally. Then here I open the switch. But if I open the switch, you don't have to follow the analog circuit design or something similar to understand that if you open the switch, this capacitor, for this capacitor is no more possible to discharge. So the charge in the capacitor remains constant, and so here we have a value that is constant. Then when I close again the switch, the capacitor will start again to discharge. The same for the delta in this point is exactly the same. I will show you what happened in the middle, but let's start from these 2 points. So exactly the same concept of the previous one. Then let's try to go on and reconstruct the weighting function. So again, Tm measurement, take the 1 point alpha 1, I take the delta, I write the delta response of t minus alpha 1. I know that here I cannot discharge the capacitor, so the value is constant. I write all the delta response, then I take this value and I report this value at alpha 1, exactly like in the constant parameter filter. I repeat this behavior for all the points. So, for example, I can do the same here. Then I will have this discharge. Here is constant, not so much constant in my plot. Then we will have a discharge here. So I have to go here and report this new value here, and so on for all the different time. The point is that what happened here, take you some seconds, 10 seconds, to try to understand what happened here, which is the weighting function, because I understand that here I will have something like this one, I suppose, because it is like the old one. Here I'm reconstructing something that is this one. But what happened here? Are you able to tell me? Okay, if I write the weighting function, I will find that here I have a value that is equal to 0. How is possible? Why it is not constant? You have just to apply the definition that we found in this slide. In order to find the value here, what do you have to do? Simply, you have to put the delta here. If you put a delta here and write the weighting, the delta response shifted in this point. Okay, but which is the delta response here? Here I am applying delta on the input, but the problem is that the switch is open, so nothing happened at the output. So I apply a delta here, but the delta response is 0. And so it's 0, and so it's 0 also when I close the switch, because nothing happened. Then it's 0 here, and so is here, it's 0 here. Simply. So at this point here, the weighting function is always 0. That's it. Okay, let's try to compute another time variant filter. Instead of having a switch that is closed, open, closed, try to reverse the switch. So we take a switch that is open here, closed only during this period, and opened here. The question is, are you able to write the weighting function exactly follow the same procedure? So take your time, like during the tutorial, and try to write this, stop the video obviously, and try to write this weighting function. If you understood the procedure, if you are able to go on, you should be able to write this function. So try. Okay, let's go on and let's try to see which is the result. How I can do that? We could start from this part here, for example. In this part here, the switch is open. So if I apply a delta here, nothing happened. So I suppose that the final weighting function here, I will have 0. What happens if I apply a delta here? I will have the delta response shifted. So the delta response is this one. Then I open the switch, so the value is constant for all the time. So I find the value at Tm, and then I move in the alpha 1 position. The same for another value. So if I'm here, a delta here, for example, I calculate the delta response starting from here. That will be something like this. Should be something like this, obviously. But the problem is that I'm opening the switch here, so the value has to remain constant. So I have this value here that I move the correct position, so something like this. If I calculate all the points, I will obtain this function here. Obviously, in the real world you don't calculate hundreds of points. You will understand that calculating just a couple of points you can understand how write all the weighting function. So in the beginning of this course, I stressed you that we have to see all the things, all the feature of a signal filtering and so on, both in the time domain and in the frequency domain. So we calculated the weighting function in the time domain. The question is it possible to calculate the weighting function also in the frequency domain? The answer obviously is yes. So let's try to do that. So what we have to do? We use again Parseval theorem. The Parseval theorem gives us this expression. So a way to write, to pass from the time domain to integral from minus infinite or plus infinite of a function squared to the frequency domain. We can extend this theorem also to the product of two functions. So the product of two functions here from minus infinite to plus infinite is equal to the product of the Fourier transform of the first one times the Fourier transform of the second one calculated at minus f. So why is important in our case? Because we have something that is similar. Because if we write the output in the time domain, we know that is the integral from minus infinite to plus infinite of the first function, the input x, times the weighting function. So we can, using the Parseval theorem, the extension of the Parseval theorem, we can write that is the integral from minus infinite to plus infinite of the Fourier transform of the input times the Fourier transform of the output calculated in minus f. So it means that we can calculate the output both as a sum of the weighted instantaneous input in the time domain, or the weighted sum of Fourier components in the frequency domain. From the filtering point of view, we will use both these situations because are both important for our work. So, just a summary of the weighting function and the summary of this lesson. Some point. First point, with a constant parameter filter, the weighting function is simply the delta response function reversed and shifted. Pay attention, reversed. Why I'm stressing you with reversed? When we will study the optimum filter, I will show you that we would like to have a function with a certain shape. And we will find that the shape is exactly the reversed of the shape that we can easily obtain with the low-pass filter. During the exam, in a lot of time, you confuse the optimum filter with the constant parameter filter. Why? Because you forgot that in the constant parameter filter, you have to reverse the delta response. So again, please remember, you have to reverse. At this moment, it seems not so important, but it will be important in the future. So, this is for constant parameter filter. For time variant or not constant parameter filter, you do not have a unique delta response because it depends on the measurement time. We saw that in certain point is 0, in other points is different value. It depends on the measurement time. And normally it's not so easy to calculate the weighting function of a non-constant parameter filter. It's absolutely not so easy. For certain filter, when you have just a switch that you open and close, okay, in that case it's much easier and it's possible to calculate and simply compute the weighting function just calculating the value for when the switch is open or when the switch is closed. So, but this is only some, as I can say, some very easy and lucky example. So, we pay attention when we open the switch and when we close the switch to the value of the electrical variables, voltage and currents, before and after the switching. It could be also not. You have to check that they can be discontinuous, for example, because we are open and close in a very fast way a switch. So These are the key point of the filtering signal. Just the concept of weighting of the weighting function, how I can construct the weighting function for the constant parameter filter and for the non-constant parameter filter. So in the next lesson we will make a summary of the filtering the noise, and I have to admit that is a long list of formula, because we will have to understand what happened to the filter, to the noise when we filter it, for constant parameter, not constant parameter, white noise, not white noise, and so on. But that will be the last lesson about the tool. Then we will start to move in with the filtering, low pass filter, high pass filter, baseline restorer, all the kind of filter, and then in the last part of the course we will apply this filter playing with the sensor, photodiode, PMT, strain sensor, and so on. So as usual, in the chapter number 6 here you can find exactly as usual how you can reconstruct the weighting function, all the things that we studied in this video, and also the demonstration of the passive. So, and for this lesson it's all.